The purpose of this video is to explore the topic of solving systems of equations graphically. Now, this is a topic that you've explored before, both in 8th grade and in your freshman algebra class, but we're going to take some of these ideas that you've learned and extend them or blend them together with some concepts and ideas that we've studied so far this year in geometry. I'm going to go ahead and start by jumping right into this first example, and we will go ahead and get busy with it. First things first, the directions ask us to solve this system graphically. So it's important that we understand exactly what it is that we're trying to accomplish or achieve by solving graphically. Really, what this says to do is says plot both equations on the same set of coordinate axes and find the point or the points where they intersect. That's what we're looking for. So what we're going to do is one at a time, we're going to graph these equations. And then we're going to do exactly what we said. We're going to find the point or the points where they intersect. So I'm going to go ahead and start with this first equation, this y equals x squared minus 8x plus 7. Now I know he's not a line because he's not in the form y equals mx plus b. I do know that he's a parabola because I remember that general form of a parabola from my algebra class last year. So in order to graph a parabola, I'm going to grab my graphing calculator. You should too grab your graphing calculator and graph these equations on your calculator while I graph them on mine. So I'm going to go ahead and pull up my TI Nspire. I'm going to go ahead and hit the home key. I want to open a new document, choice 1. And then choice 2 asks me what I want to add. I want to add a graph. And in for the first function, I'm going to input the equation of that parabola. So I've already got my f of x equals. I want to type in x squared, subtract 8x, and then to that add 7. And then if I hit enter, it draws me a pretty little parabola. Notice that at the bottom, I can't quite see my whole parabola. So I'm going to need to extend my viewing window, and I'm going to do that by going into menu, and I want to hit choice 4, which is window or zoom. I could zoom out, but I like to set my own window setting, so I'm going to go to choice 1. I like the minimum and maximums for the x. I like a -10 to 10. I'm actually going to come down here for the y's and make the y minimum -10 and the y maximum 10. And this doesn't always give us a nice viewing window, but for the most part now we can see that entire parabola. Somehow we have to get this parabola from our graphing calculator onto our graph. And the way we do that is going to be to examine the table. Now hopefully you remember from the last couple of years how to get this table, but if you don't, you can just hit Control-T and it'll pull up your table for you. So there's our table. And I'm going to scroll through this table until I get some good values to graph. Kids will say, well, how many places or how many points do I need to include in my table? And my answer to that is a definite, it depends. You need to include as many as you need to include so that you can graph a very accurate picture of what is going on with that parabola. Now, I need to see on your paper your table of points with values that you use for this parabola. So you're going to come back to your page in your notes, and you're going to make me, each and every time you graph a parabola, a table of values for x and for y. So from my table, I got the point 0.07. From my table, I got the point 10. 2, -5 is on that parabola, as is 3, -8. 4, -9. 5, -8. 6, -5, 7, 0, and 8, 7. And those points taken together will give us a very clear, very accurate picture of exactly what this parabola looks like. So I'm going to go ahead and plot these points. And now that I have a clear picture of where I'm going with this parabola, I'm going to take my pen and I will connect those points with a nice smooth curve. I'm going to keep in mind that just because my table ends at 0 and at 8 doesn't mean the parabola ends. So I'm going to put a little arrow on there to indicate that this parabola does continue onwards. And I'm going to label them with this equation. Y equals x squared minus 8x plus 7. So there's my parabola. The next part I need to graph is I need to graph this equation x minus y equals 7. The first thing I need to do is manipulate algebraically so that it's in the form y equals mx plus b. So I'm going to go ahead and start by subtracting an x from both sides. So a minus y is equal to a minus x plus 7. And then I don't want a minus y, I want a positive y, so I'm going to take the opposite of each and every term in my equation. So y equals x subtract 7. So this line has a slope that's equal to 1 and a y-intercept of negative 7. So I'm going to go ahead and come over here to my graph, and I'm going to find the y-intercept of negative 7. And then figure out where a line of slope 1 would go. That's up 1 to the right 1. And then I'll grab my straight edge because I want to be as precise as I can possibly be when I'm drawing these so that I can look for good points of intersection. And I'll draw my line. I'm going to then go label my line with this equation, x minus y equals 7. So my whole point, my whole purpose in sketching these on the same set of coordinate axes was so that I could figure out the point or points where they intersect. The coordinates of those points are the solution to this system of equation. So it looks like these two graphs intersect at the point, first of all, whose coordinates are 2, negative 5, and also at the point whose coordinates are 7, 0. Notice that each and every time I write an ordered pair, I write it surrounded by parentheses, and you should be representing your ordered pair surrounded by parentheses also. We want to attend to that precision and make sure that we're including the details that allow us to communicate mathematically with mathematicians from all over. So make sure that you're not taking shortcuts and leaving those parentheses out. Now, if I wanted to go ahead and to graph that on my calculator, I could go ahead and graph that line right with my parabola. I'm going to go ahead and hit Control-T to get rid of that table that I put in there. I've already got my parabola on there. I'm going to hit Control-G to go put another graph on the same coordinate axes. In this one, his equation is y equals x minus 7. So I'll just type that in there. Hit enter, and now I'm pretty sure that I did indeed graph this system correctly. Now, if this were a multiple choice question and all they were looking for were the points of intersection, I could have done this question entirely on my calculator. To have my calculator figure out the points of intersection for me, I'm going to go into Menu, and under Menu, choice 6 says Analyze Graph. And what I'm looking for here is the points of intersection, so choice 4. And notice that once I select choice 4, it puts a vertical line on my graph. It's looking for what it calls a lower boundary. So I'm going to move just to the left of where that first point of intersection is, and I'm going to hit enter. It's going to ask me for an upper boundary. I'm going to move it over and hit enter again. And it tells me very clearly that the point of intersection is the point whose coordinates are 2, negative 5. I can go do the same thing for this point of intersection over here as well. So again, to Menu, choice 6, Analyze the Graph. I'm looking for choice 4, a point of intersection. And I want to move that just to the left of the point of intersection. just to the right of the point of intersection. And it verifies what I already knew from looking at the graph that I made. It verifies that that point of intersection is the point whose coordinates are 7, 0. All right, so there's example 1. I think in the interest of time, we're going to do example 2 solely on the graphing calculator. So I'm going to go ahead and take a look at this first equation. I'm thinking it's a parabola because of the exponent of 2 in there. And because this is already in the form y equals, I'm all set to go ahead and put this into my graphing calculator. So I'm going to boogie over to my graphing calculator. I want to start brand new, clean, fresh with a new graph. So I'm going to go ahead and go home. I want to go to a new document. And as beautiful as that first system was, I'm not going to save it. And I want to add a graph. So to input that first function, I'm going to input it exactly the way that I see it on my paper. Again, it's already in the form y equals, so I'm ready to go here. I'm going to go ahead and type in y equals x, subtract 2, close the parentheses, square it, and then from that I want to subtract 3. And I've got a really nice viewing window already. I don't have to do anything to that in order to make it prettier or better. I've got a good solid view of what that parabola looks like. So now I need to go ahead and graph the second equation in my system. And the second equation is going to take a little manipulating before it's in the form that I want it to be in. So I'm going to go ahead and subtract 16 from both sides. And then to undo this multiplication by 2, I'm going to divide each of the terms by 2. So y equals 2x subtract 8 is the equation that I want to put into my calculator. So again, to add a second graph, I'm going to Control G, and it gives me the option now to enter my second function, and that is y equals 2x subtract 8. Wow, that's interesting. So I'm looking at this saying, wow, I'm really not quite sure exactly where those two intersect. And maybe had we drawn this graph on paper, we would have found it very difficult to tell from our graph exactly where these two intersect. So I'm very lucky in that I have done this on the graphing calculator, and I can go in and I can find that point or the points of intersection on my graph. So I'm going to go move that till it's right to the left of the point of intersection, move it until it's right to the right, and my calculator confirms for me that the point where these two graphs intersect is the single point whose coordinates are 3, -2. So we kind of took a shortcut on this one in the interest of time. If we had solved this graphically, we would definitely need to use this graph. There would need to be a parabola and a line, both labeled appropriately, with the point of intersection identified as 3, -2. But again, in the interest of time in making the video, we're going to bypass drawing the graph for right now. So kids will often ask me, they'll say, well, how many solutions am I looking for? The first system that we did up at the top of the page had 2 different solutions. This example down at the bottom of the page only had 1 solution. And if we flip up to the top of the next page, I want to know, do all quadratic linear systems have exactly 2 solutions? Well, we know that that answer to that is no. We saw one who only had 1 solution. Can you sketch an example of a quadratic linear system that has exactly 1 solution? Well, again, we saw one down at the bottom of the preceding page. So I guess the question would be, can you draw one that has no solution at all? And I'm going to leave that question kind of open-ended, and we can talk about that the next time that you come to class. In the meantime, I want to go ahead and take a look at number 4, because this is where geometry kind of integrates with what you've seen before with respect to systems of equations. This first equation here in number 4 says x squared plus y squared equals 9. And this is new, it's different because it's not a line, it's not a parabola. You got it. This is the equation of a circle. In order to graph a circle or to write its equation, we need to know 2 things. We need to know the coordinates of the center of our circle, And we also need to know the length of the radius of our circle. For some reason, again, the ghost has taken over my computer and is doing all this fancy writing. Not quite sure how that purple scroll got in there. Let's see if we can't make it go away. Well, I guess we're stuck with it. At any rate, we said its center. Well, its center is going to have coordinate 0, 0. His radius is going to have length of 3. All right, so I'm going to go ahead and head over to my graph now. His center is right here at the origin. His radius is of length 3. In order to be as exact as I can be, I'm going to dig my compass out, and I'm going to draw this circle. So there's my circle, and I'm going to label him with his equation, x squared plus y squared equals 9. And now that my circle's graphed, I'm going to go ahead and put my compass away, and I'll go graph the second equation in my system. In order to graph that line, y plus x equals 3, I'm going to subtract x from both sides. So y is equal to minus x plus 3. So my line is going to have a slope of -1 and a y-intercept of 3. So I'll head over here. There's the y-intercept of 3. Slope of 1 means down 1 over 1. I want to go in a negative direction. So now that I have a good feel for where that line should go, I'll grab my straight edge. And I can go ahead and graph that line. And I'm going to label him with his equation, y plus x equals 3. Let's remember that the whole point in drawing this graph was to find the point or the points that these two share, that they have in common. Where do they intersect? So there's one solution right there. There's a second solution. And I'm going to very clearly on my paper identify those two solutions. The first is the ordered pair with coordinate 0, 3. The second is the ordered pair with coordinates 3, 0. All right, so there's a system of equations that doesn't involve a parabola, but rather involves a circle. Don't let the fact that it doesn't involve a parabola mess with your head. You're going to solve it exactly the same way you would if it were 2 lines or 2 parabolas or a circle and a parabola. Put them both on the same set of coordinate axes. Make sure you label the graph. Find the point or the points where the two intersect. All right, and looking down the page, I want to know in number 5, do all systems that involve a circle and a line have exactly 2 solutions, like the one that we graphed in example 4? Can you sketch one that has exactly 1 solution? Are there any out there that don't have any solutions? That one, too, I'm going to leave to you to think about. We'll talk about your thoughts on that the next time that you come to class. And example 6, I think we're going to leave also for when you come back to class, and we'll figure out if Susie is knowing what she's talking about or if she needs some help from us. All right, as always, thank you for the gift of your time. I hope that you got something out of watching this video and that it either enhanced some learning that you already had or maybe cleared up some misconceptions that you might have had from the previous times that you solved systems of equations. But as always, if you do have questions, please jot them down in the margin or feel free to shoot me an email.